to find their way.
The problem we're talking about is the problem of a ship at sea that doesn't know where it is. Or at least it doesn't know where it is well enough to avoid running onto something hard and pointy. So what GPS does in a very economical way is give you the answer to that problem.
GPS, the Global Positioning System, is a constellation of navigation satellites. Brad Parkinson directed the effort to design these satellites and put them in orbit.
Basically what the ancient, more or less ancient navigators would do is measure the so-called elevations of stars, which is the angle from the local horizon up to a star or other heavenly body. And in order to have that particular angle, it turns out there was a circle on the Earth that only could have that angle. And by mathematically working that out and looking at several of these bodies, they found their intersection at, in essence, arcs of these circles. GPS doesn't do that at all. The math is quite different, and the results turn out to be quite a bit better.
Next exit on the right, followed by slight right turn.
Using distance measurements instead of angles, GPS is revolutionizing our ability to navigate the Earth.
We should be going beneath the underpass in the relative level. It should be loop road.
A new system links a car's real-time location to a digital map.
Right turn ahead.
A mapping team is checking important details by comparing the display to what they see out the window.
Left turn ahead.
And that would be Cortland. And it is a one-way southbound. We're good.
As the car winds through a maze of freeways, an onboard receiver detects radio signals from satellites 11,000 miles overhead. Clocks in each satellite are synchronized with each other and broadcast coded time signals to the Earth below. The car's receiver compares the arrival times and computes the distance to each satellite. Each distance defines an imaginary sphere around each satellite and pinpoints the car's location within several feet.
Please proceed to the highlighted route.
To locate the position of the car, the location of the satellites must be known precisely at every moment.
Lieutenant Crooks, could you verify that the SVN-9 pass is scheduled to start at 1900 for a stored state of health?
At Falcon Air Force Base in Colorado, 24 GPS satellites are monitored on orbital paths first described by Johannes Kepler over 300 years ago.
Math is at the heart of this system. Kepler, of course, worked out several laws, and these laws reflect how spacecraft move in orbit. And he discovered things that were mathematically very elegant. They move in ellipses.
But satellites do not move in perfect ellipses because the Earth is not a perfect sphere. Over tall mountains, the pull of gravity increases. Over ocean depths, the pull is less. These forces cause satellites to drift up and down several miles from their elliptical orbit.
What GPS has shown itself able to do is predict within meters where the satellite will actually be. That mathematical description is stored in the satellite and broadcast to the user. In essence, the satellite is hollering down, "I am here, I am here," and the user says, "Yes, now that I know you're there and I know what time it is, I can sort out where I am."
Left turn ahead.
With GPS, timing is everything. Onboard clocks are built to measure signals moving 186,000 miles per second.
These clocks are stable to the point they lose at a rate of no more than 1 second in 300,000 years. Why do you need such accuracy? Because they are basically timing a signal that's being propagated with the speed of light. 1/billionth of a second, or a nanosecond, is equivalent to 1 foot. Modern man takes a lot of things for granted. Man in the 17th century could no more conceive of going faster than a horse than flying to the moon. Well, what has now happened is we have a new power. That power is knowing where you are.
Left turn ahead.
I would categorize the math that's embedded in this, as elegant and wonderful as it is, as another example of something that modern man will take for granted. It's invisible. Someone can push a button. The math is embedded in this little chip. It gives us our answer. Here we are.
With mathematics, we have mapped the Earth and created heavenly bodies to guide us across its surface. Understanding the Earth's geometry has made the planet a familiar place, and scientists are now using this knowledge to explore a realm that is far less familiar: the universe itself.
The Earth is sort of flat, but you wouldn't notice it if you were coming up this road. Yeah. But on the big scale, of course, if you look at a globe and the mountains are all to scale, they're barely tiny little ripples on the surface. The Earth, even though it has relief on it, on the big scale, what it really is a sphere. It's the same sort of thing when you're doing an astronomical measurement. So you come to a place like this where you have the big instruments and where observing conditions are very good, because we want to work on very faint objects so we can measure big chunk of the universe, a big enough chunk so that it begins to reveal its geometry.
For the Greeks, the challenge was to discover the Earth's shape without seeing it whole. Modern astronomers face a similar challenge. Many scientists, including Einstein, have theorized that the universe may be curved, like the surface of the Earth. Robert Kirshner is taking measurements that may reveal its actual shape.
We don't have a ruler that we can stretch from one place to another, so we have to use a more indirect distance measuring tool.
Kirshner and his colleagues are mapping sections of the universe. Like other map makers, he needs mathematics to deduce one measurement from another.
You can take a picture of a star or a galaxy and you can see its shape, how it's distributed on the sky, but one of the more powerful tools that we have is to take that light and run it through a prism or a grating that spreads the light out into a